Welcome, everyone. If you're an engineering student who really wants to learn the nuts and bolts of dynamic system control, you are absolutely in the right place. Today's explainer is a meticulously detailed, step-by-step masterclass based on some truly phenomenal material provided by Dr. Nima Madian. We're not going to skip a single crucial term here. We're going to take all that complex, chaotic theory and transform it into highly practical, real-world engineering logic. So, let's just dive right in.
Here is our roadmap for today. We're going to start with the challenge of dynamics, break down the actual anatomy of a system, and then explore the universal control loop. After that, we'll compare feedback versus feedforward strategies, look at an ultimate combined architecture, and finally translate all of this mathematical logic into physical hardware components. All right, Section 1, the challenge of dynamics. Let's ground ourselves in exactly why control engineering even needs to exist in the first place.
Look at that wild, fluctuating orange line. That right there shows you just how chaotic an unmanaged system actually is. You see, real-world processes are inherently dynamic. They're constantly drifting because of shifting internal states and totally random external forces. If you just set up a system and watch it work once, yeah, that is never enough. Without continuous active supervision, these processes will drift and completely destabilize. Control engineering exists because we absolutely require that continuous supervision to force a process toward a target and actually keep it there despite constant, unpredictable disruption. Which brings us nicely to Section 2, the anatomy of a system. Because before we can ever hope to control a process, we have to rigorously define it. Every single system is built on a foundation of variables. Let's go through these carefully so we don't miss anything. First up, input variables. These are the independent variables that stimulate our system. We use them to deliberately induce a change. Next, we have output variables. These are the measurable characteristics that reflect the results. They give us the crucial intel on what just happened. And finally, state variables. This is the absolute minimum amount of data you need to completely and accurately define the exact internal condition of a system at any precise moment in time. Building on those exact definitions, let's take a look at the process block itself. We have to draw a hard line between what we can control and what we can't. On the left side, those blue arrows, those are our control variables. These are the inputs we actually have the power to physically manipulate. But coming down from the top in orange, those are disturbances, uncontrollable, chaotic forces hitting our system from the outside world. Ultimately, our outputs on the right are the direct result of a continuous battle between our deliberate control variables and those random incoming disturbances. So now that we know our variables, we arrive at Section 3, the universal control loop. This is the beating heart, the dynamic engine behind all automated control. Back in the day, you literally had a human operator standing by a valve, manually tweaking it. Today, we've replaced that person with a blazing fast, continuous cycle: measure, decide, act. We measure the real-time outputs. We decide on a corrective action using mathematical logic, and then we act, physically executing that decision through our control variables. Measure, decide, act, over and over again, in a matter of milliseconds. When we set this continuous loop in motion, it's pretty amazing. Feeding the measured output right back into the decision-making brain of the system means we are constantly fighting back against those uncontrollable disturbances we just talked about. The system literally never sleeps. It's always correcting, always adjusting, always fighting to keep things perfectly stable. But this introduces the great dilemma of our field, which brings us to Section 4. When we're designing this control architecture, should we be reactive or should we be proactive? Let's examine our first strategy, feedback control. This is the reactive standard. It monitors the output at the very end of the process and basically waits for an error to manifest, meaning a deviation from our target, before looping back to adjust the input. Now, it's highly robust and it's totally self-correcting, but here is the catch. It inherently has to wait for a mistake to actually happen before it does anything. It's always fixing the past. Now, contrast that with strategy 2, feed-forward control. This is the proactive alternative. Notice how the sensor here is measuring the disturbance before it even hits the process. It uses a complex mathematical model to predict exactly what that disturbance is going to do and instantly adjusts the control variable to cancel it out preemptively. It is incredibly fast. But, and this is a massive but, it is completely blind. If an unmeasured disturbance sneaks in, or if your math is even slightly off, the feed-forward controller won't even realize an error is happening. So when do you use which one? Think of this as your quick study guide.
Feedback triggers off the error. It's reactive, and honestly, it requires very little knowledge of the system mechanics to work. Feedforward, on the other hand, triggers off the disturbance. It's proactive, but it requires a phenomenally high level of mathematical modeling. Basically, you want to use feedback for slow, complex, unpredictable drifts, and you use feedforward when massive, fast-acting, measurable disturbances threaten to just instantly derail your entire process.
So which one is actually better? Well, that brings us to Section 5, the ultimate combined architecture. Because honestly, why choose one when you can just eliminate the weaknesses of both? Let's look closely at how we build this out. The absolute gold standard for high-performance industrial stability uses both strategies together. We deploy feedforward at the top to measure incoming disturbances and act with predictive agility, canceling out massive shocks instantly. But at the exact same time, we run a feedback loop at the bottom to monitor the final output. That feedback loop ensures total, precise accuracy over time, correcting any minor, unmeasured drifts that our feedforward model might have missed. Let's ground all this abstract theory into physical reality for a second. Picture high-intensity industrial furnace. If a sudden surge of cold fuel enters, that's our inlet disturbance, right? A simple feedback controller wouldn't react until the entire furnace actually dropped in temperature. But with our combined architecture, a flow sensor preemptively detects the fuel change and adjusts the valve instantly. Meanwhile, the temperature sensor at the exit is still providing feedback to perfectly fine-tune that long-term heat output. And just look at this staggering difference in performance here. The red line, that's uncontrolled failure. The yellow line is feedback only. Notice how it wobbles widely as it reactively hunts for the target before it finally settles down. But look at that green line. That is our combined architecture. The exact moment a disturbance hits, the combined system achieves almost instant, incredibly tight correction. We are dramatically reducing both the maximum deviation amplitude and the total settling time. It's brilliant. Okay, we've mastered the logic. Now, for our final section, translating logic to hardware. How do we actually map these mathematical loops onto cold, hard, industrial equipment?
I absolutely love this part because we can use a biological metaphor to perfectly understand how these industrial components function together out there in the real world. Think of it exactly like this. First, we have the sensors. These are the eyes of the system, responsible for the continuous physical measurement of our variables. Second, the transmitters. This is the nervous system, rapidly carrying those data signals across the entire architecture. Third, the controllers. This is the brain, where the actual logical algorithms live to decide on corrective actions. And finally, the actuators, like heavy motorized valves. These are the muscles. They do the heavy lifting, physically executing the required change to our control variables. Eyes, nerves, brain, muscle. Measure, decide, act. And there you have it. You've walked step by step from the chaotic reality of unmanaged systems all the way through advanced combined architectures right down to the physical hardware. Now that you truly understand the anatomy of dynamic systems and exactly how to wield both feedback and feedforward control, my final question to you is this: what chaotic real-world process will you engineer into stability next? Thank you so much for exploring this with me today, and a massive thank you once again to Dr. Nima Mahadian for providing such a phenomenal framework. Keep building, keep controlling the chaos, and I'll see you next time.